Test. Do you hear me? All right. Good morning, everyone. Thank you for the invitation and the introduction. It's a pleasure to be here and talking about stuff that are really, my opinion, and I hope that manage to communicate this interest and this excitement to you as well. So the topic, as Kazim was saying, is mostly big data and machine learning. In fact, it's mostly deep learning. This is the keyword that's going to be describing the whole underlying theme of today's tutorial, and the application in remote sensing. So some information from Kazim already said about the information. My background is in electrical engineering. I did a PhD in magic science, and I have been collaborating with Madam Otagam here at USC for a few years now on machine learning and microwave and remote sensing. Right, so this is to get things started. This is where I'm coming from, and the challenge here is how can you drive all around this and then end up in your office here and do some research. But we manage, right? So it's a struggle. So that's here, right? It's in the Mediterranean. It's a beautiful place. But there is also significant research happening there. A lot of people that she's making some international profile in terms of their research. So both this is the Foundation for Research and Technology Analysis, the research center that is there, is composed of a number of institutes. It's 10 now. One of those which cover these topics, like from electronic plates and structure to molecular biology, applied mathematics, astrophysics, and computer science, which is my domain. And within this domain, there is the signal processing lab, one of the main labs that is the lab that hosts me, and I'm part of this team here. It's a fairly small lab, but we're very active in this domain. And special thank you, to all the people that have been collaborating all these years. Panos Tsakalitis is head of the lab. Madam Otagam here, special thanks. And Zandok Stark. So Zandok Stark is an astrophysicist, very well-known astrophysicist and signal processing, data analysis, astrophysics type of guy. So this is meant to illustrate that a lot of the ideas that we see today that applies to remote sensing, which typically when we think of remote sensing, we think of satellites on the monitoring the Earth. We turn the satellite the other way around, in deep space. And there's a lot of interesting stuff and a lot of parallels between the things that we do, let's say, in the more traditional Earth remote sensing compared to what they're doing in astrophysics. And also shout out for the collaborators here. And of course, funding is important. So this Marie Curie Fellowship. There's another project now that started. It's called Titan, which is the idea of developing what's called astroinformatics. So introducing AI and the analysis of astrophysical data. These projects, that we're going to be discussing about today, have been funded by the European Space Agency as well as ESA. Right. So this is a short introduction of who am I. And so what's the plan for today? So the plan for today is for people that have a basic understanding of the idea of analyzing data and getting observations, to come up with some basic understanding of what machine learning and deep learning is and how it can be applied in remote sensing data analysis. So in order to cover this, the class today is structured in 4 sections. So the first section has to do with some motivation of what's happening now and why is this topic more popular now than it was 10 years back, and the introduction to deep learning. The second session is on the discriminative models. This is what you probably have heard of. It's the classification type of problems, right? So you're giving an image and trying to say whether this is going to contain a couple of dots, a classification problem. So this is the thing that we're going to be trying to explore. And then at the end, there is sort of a hands-on, small hands-on. So to minimize, the efficiency in terms of time, I have prepared some stuff. And so GitHub, and I will send you the code, the link, where you can download. So there is some code that implements one of these examples. One of the examples of image classification is a step-by-step code. So I will try to explain the code so that you can understand what's happening there. The code is available online. You can run it yourself, and I can tell you exactly how you can run it with minimal requirements in terms of setting up environments and things like that, so you can run it online only. Then the third part is on what's called generative models and inverse problems. So if you like to describe this topic, these topics related to enhancement. So you're getting remote sensing observations which are noisy, they have some artifacts. how can you take them, apply these deep learning or machine learning ideas, and get something which is higher quality. And in the end, there is hands-on on how we can use networks and systems like today for denoising images, so one case study. And then the last section, which is sort of also there's some buffer there in terms of like distributing the timeline, is some extra topics that have to do with what's happening now, some more less well-known topics, and what's the interaction, what's the relationship with what's happening now in terms of AI overall and the whole excitement about this domain. You're free to ask any questions. You please interrupt me. So the whole idea is to get an understanding. So you're going to get hopefully the big picture, the key ideas. But of course, there are a lot of stuff that we're not going to be able to cover there. This is a whole semester class. But feel free to interrupt me. Right, so the first thing to start to say, okay, so the motivation. So why would I care about machine learning and deep learning and AI and how they apply in remote sensing? I've been doing remote sensing for many years. They didn't really need to go into this type of problem. So what's happening now is that there is a convergence between different trends in terms of technology. So one of these trends is what's called the big data. So big data is the idea that we're getting so much information there that there are challenges that are characterized by the fact that it's not just the data, it's the scale of the data that also makes a difference. So in terms of scale, some of these issues that make standard data, big data, has to do with the fact that typically the volume is huge, right? So you have remote sensing observation from Sentinel and Landsat, covering the entire line every 2 days, so huge volume of observations. You have variety, so you have optical sensors, you have radar sensors, you have other type of sensors. How do you reconcile them? And then there are veracity. There is the question of so I get an observation. So how reliable is this observation? I'm extracting some information about the environment. How good is this quality of extraction? Velocity, it's similar to volume in the sense that there's a lot of information being produced all the time, and all of this, the whole idea is to put them and extract value, right? So can I use all this, consistent stream and source of Earth observation that's happening right now to get something that's going to create value, scientific value, societal value, economic value. So this is the whole idea of big data. And if someone wants to give a sort of it's so why today? So we have data. So what makes big data something relevant today? So you can think about stuff, comparing what happened, in terms of the overall society, right? And social aspect of the whole idea. What was happening in 2017 in a minute, right? So you had 46,000 posts uploaded in Instagram and tweets and blah 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 and Netflix, and you can compare that with what's happening in a few years, right? So we went from 40,000 posts in Instagram to 500,000, right? So you see a situation where you have order of magnitude increase in terms of presence, in terms of data, right? So you say, okay, so we have a lot of Instagram images. Why is that the thing? So, if I'm a company and my idea is to use this information that's encoded in these Instagram images and come up with a new hype or the new trend or the new, whatever thing I'm trying to sell, trying to find a way of understanding this amount of data is critical, right? And it's not obvious how to do that. But in addition to this societal aspect of big data, what is more interesting in terms of us, the scientific and engineering community, is how this problem applies also to the terms of what's called big science data. So scientific observations that come from instruments, scientific instruments, satellites, for example. And so one example is physics. So this is one of the things that I'm working on, but it's not the focus of today's talk. So you see what's happening now is we're moving from satellites and space observatories that would focus on a specific area in the sky and then focus on that and take long exposure to stuff like that, to new type of instruments and new type of surveys that try to cover the entire sky every night or every night, all the way to this is a very interesting. This is a square kilometer array. It's a radio wave observational system, and this is going to produce. This is called exabytes, right? So humongous bytes, right? So it's a huge amount of data. So people are designing this SKI now know that 90% of the observations are going to be thrown away. They know that now by design. There's the observations, we're going to do some correlations, we're going to do the interferometry, and then we're going to throw away 90% of the observations because that's too much, right? And keep only the most interesting. And the same thing happens in Earth observation, and this is driven by the fact that we have truly an exploding number of Earth observation satellites coming online. Now we're moving from typical satellites to constellations. And communication is one thing, but Earth observation is also experiencing this blooming in terms of satellites and constellations. And at the same time, where we have more of them, we have lighter of them, right? So the average size of this satellite is reducing. So exploiting the miniaturization of technology, driven to an extent from the smartphone and all this technology, we can cram up a lot of technologies in a very small box and then deploy them. So the cost becomes smaller. I have the opportunity with the same budget, instead of having one big industrial satellite, get 10 very small of them and increase my release time and things like that. So there's a lot of merit in doing that. So you have all this huge amount of data, and you can follow like standard sources like NASA and European Space Agency, but also private companies like Planet, that they can capture the entire planet every day or every few hours. I don't know what's the rate now. So huge amount of data, and this problem of data also applies to the case of Earth observation, right? So you have again a variety of sources, from satellites and drones to buoys and in-sensor networks and all this type of sensors that we can integrate, and they fall under the remote sensing paradigm. And you need to take them all into account and make sure you extract information and all the knowledge and whatever is critical to be extracted from this data. It's not an obvious task, and especially when we're trying to do these tasks at scale. Right, so when we talk about, so let's say I sort of convinced study yes, we have a lot of data in Earth observation and in science in general, and we'd like to analyze them. Right, so what we're gonna do, spoiler alert, we're gonna apply machine learning. But to start with this discussion, the very first thing is like, what about the data? So what's the source of the data we're gonna be using? Right, so in terms of data, which is a critical aspect because this will define what type of analysis and what type of information we can extract, there are different types of questions. For example, are we talking about an active or a passive imaging system? How many spectral bands are encoded there? Is the system doing what's called global coverage? So is it more like Landsat that covers the entire planet every few days, or is it more like a private company that tasks the satellite to look at a specific region because there's a customer paying for that? So that makes a difference. So again, the data are they private or they public? And then is this a new mission, and are we getting new data, or is the historical data that can go back like a standard Landsat type of scenario that we can exploit? And so active versus passive, the whole idea is that in active sensing, what you're doing, passive sensing, what you're doing is you're capturing the reflections, the natural reflections. So you get images which look like that. It's a big spectrum, but you can create red, green, blue type images that look really like the information you get from a camera. And then you have active systems, such as radar and SAR, which you get observations like that. That's more difficult to interpret. It's not as clean. But you have a lot of added value in this type of technology, in the radar technology, in the fact that it is robust against weather conditions. So this system fails if there are clouds. So you cannot image something under clouds, but with radar you can. And then you can image day and night. So there are pros and cons in its technology and what it offers. And the next question is like, okay, so I'm gonna use a source to transmit information and receive it, or just receive the reflections. The question is, what is the wavelength, right? So which is the spectral band, the spectral region we are interested in? And this is important from a remote sensing point of view because different materials give a different spectral profile. So snow versus asphalt versus water versus dry grass. So if the whole idea is to get observation and understand what's happening on the planet, getting as much as the more information you get across the wavelengths, the more information, the more intuition and the more understanding you're going to get from these observations in doing your task, classifying blood classes. Right, so a couple of examples, so you probably know them. If you don't, these are the standard, let's say, off the shelf, top of the line sensing missions that you can follow today. So this is the European Space Agency Sentinel-2. This is an optical mission. It's a global coverage, so you're going to capture the entire planet in a few days. There is a reduced period, but the most important is open access. So you can go to different sources. I'm going to show you ways of downloading this data and have up-to-date observation. The spatial resolution in general, it's okay. The good bands are in 10 meters. The spectral resolution is good. So we have 13 spectral bands, so you can see the different spectral bands along the visible and near infrared spectrum. And putting those two satellites together, you can revisit every place on the planet every 5 days, which is fantastic because you can immediately start generating time series of observations and monitoring and understanding stuff that are not obvious from a single observation. So along Sentinel-2, the counter example from NASA is Landsat, and it's much more, candidates in the Landsat program. Now we have Landsat 8 and 9 now, and before that it was 7. So similar mentality, similar idea, multispectral images, again, the variance of spectral bands that you're going to observe. 16 days revisit period, similar characteristics. So you can think about those two instruments, Sentinel-2 and Landsat 7, as two very similar instruments, which means that if I have information about one, maybe I can use that when I get information from the other, or sort of try to fuse them together. Very interesting topic. And then, as I said, there are private like Pleiades Neo that they have resolutions. In this case, goes up to 30 centimeters, right? So you have 10 meters or 15 meters, or images that look like that. So you have enough estimate of what's happening, but you're not going to say individual car, let's say. In cases like Pleiades, which is the type of observations you get in Google Maps. So when you open Google Maps, the type of resolution you see here is this type of observation. Pleiades Neo and other type of sources. Those satellites. So the question is like, why don't we have information that looks fantastic, like Google Maps, but we have information that looks okay, but it's not like Google Maps. And the reason we don't do that is because these satellites are tasked. So you have to someone to pay the company to make a satellite rotate in space and take a specific images with super fantastic analysis, but that's about it. So it doesn't offer global coverage. But on the locations we get observations, the quality is MODIS is also a very, very standard instrument on board the Terra and the Aqua satellite. So this is also the case because what you get here is you get the time series type of aspect. So you have almost daily observations, very coarse resolution. So it had 250 meters, but daily observations. Right? So every time there is a state of between spatial resolution and temporal resolution. So you can either have something that's very detailed, but you need to select when you can observe it, or the other way around. You can have very coarse observations, but have it continuously every day, like it's the case of MODIS, for example. And then there are cases where you don't have a satellite, but you have an instrument like Aviris, which is aboard an airplane, so it's an airborne instrument. So in this case, what you do is you don't have you have fantastic spatial resolution, you don't have a temporal resolution because you have to fly, so it's not going to be anything. But what you get spectral resolution. So this is a hyperspectral instrument that you actually get this thing that looks like it's called spectral hypercube. So it's a 3D structure where you have spatial coordinates as like X and Y, but the third dimension is the spectrum, right? So the information that happens across a very finely sampled array of observations in a very big range of wavelengths. So it's much easier to understand what's happening and identify materials on the ground and get a better understanding of what we image from this type of observations. But again, you have to pay a price. Right? So there is a trade-off. There is no way of generating one satellite or one mission and get everything perfect. Every time you get increased spectral resolution, you pay the price in something else, temporal resolution in this case. Right, and so these are we moved from free multispectral observation, so free, limited spectral range information, but continuously and global coverage, to something that is more focused but higher quality, to something that is less focused but continuously available, to something which is not continuously available, extremely focused but offers something new. And then there is, the question is like, can we have information besides the passive scenarios we were talking about up until now? Yes, we can. So you can have Sentinel-1. So this is a radar mission. So it's a SAR, it's a C-band SAR. So what you do here, you have the satellite transmitting a signal and then capturing the reflected signal, and you have different ways of controlling the system. So these are the different types of modes that you can sort of work with satellites. So you can have like sampling, let's say, the region, or you have a spotlight type method, or you can sampling across tracks. So tomorrow you're gonna get a lot much more information about this topic. But as again, the information you get is, it takes some understanding, right? So it's not as obvious as tolerance. That's why we're going to have a class tomorrow focusing on that. And there are other cases. For example, there is the SMAP mission, which is a mission from NASA that is developed soil erosion. And in this case, what we have is we have a radio. We have this really huge antenna, and it's capturing the reflected light, but it's capturing the reflected light in microwave wavelengths, right? So you have interesting information, and this is a scenario where you design a mission like SMAP and you have some primary target application. So in this case, target application was soil erosion. So unlike a tool landscape where you develop it and you deploy it and you hope to get continuous amount of data, in this case you have a more focused application. So SMAP is one type of example. And then there's also this last case that I'm going to be talking about, which is the Cygnus mission. And the Cygnus mission is an interesting case because this is how to move from something that is either passive or active to something that is called opportunistic. So the idea in Cygnus is that it's expensive to the radar and have a transmitter on my satellite because it takes a lot of energy, but the receiver is fine because the receiver is free. So what happens if again, instead of sending signals and capturing the reflections, use signals that are transmitted from GPS satellites. So this is GNSS idea, GNSS reflectometry. The idea is you have, the GPS satellite transmitting the signal less all the time. And what you do is you get a reflection. And what you have to do is you have to, account for the reflection, the direct signal and the reflection, and see how you can get interesting information from there. Soil moisture, this mission was originally developed for monitoring cyclones, tropical cyclones. So this is a scenario where you have very control of what happens when, because the GPS satellites do their job, the reflections happen the way they happen, somebody asks you, it's not a matter of control, and you have to make sure that you dig inside those data and you somehow extract what's critical. Right, so here all these range of options, from something that is free to something that is paid, from cost resolution, high resolution, to something that works days and nights, to something that is more easy to understand. So all these information, you need to some extent be able to understand the merits and the characteristics of each type of sensor, so that you know how that applies to the specific problem you're trying to address, but also how the machine learning is going to interact with this framework. Any questions, thoughts, ideas, comments? Yes, please.
Earlier you talked about big data and data management. Do you think there are trade-offs between control and spatial resolution from a data storage perspective?
The resolution are going to be defined by the instrument itself. Right? So you design the instrument, you put the specification, that's the instrument. Then you can optimize for that in terms of data storage, but it's not like you're gonna, say, oh, look, my images are, coarse to the fine resolution, but I'm gonna, compress them very hard so that they, I save some space. I mean, it's usually, this is derived. This characteristic is derived. So you have to design the satellite, and this is where the trade-off takes place. Right? So it's like, do I want to have like a big satellite or small satellites? One satellite or many satellites? Active satellite or passive satellite? This is where you do the design choice. And after that, you try to optimize that with respect to whatever information is captured. Now, having said that, I would definitely say that this domain of the fact that we have a lot of data and remote sensing and how to optimize the interaction between those two is in its infancy right now. So the scenarios we're talking about, like yesterday we saw scenarios where you have some information in Amazon cloud storage and you can do some stuff there. Today, the scenarios we're talking about, you download the data, so you put it in a Google Cloud service, but you still need to download them. It's still not clear, how I can sort of try and use these methods where the data reside instead of compressing them, storing them, and answering questions like that, which is the most efficient one. So this is definitely still an open topic. Yes, please. Fantastic idea. Let me know. Yes, yes. So one great idea is if I have, for example, like two missions that are very similar, like Sentinel-2 and Landsat, and one passes on Tuesday and the other on Wednesday, can I do something? Yes, of course you can. And interesting topic. There are a couple of papers on that, but yes, yes. So whatever you think about this, one of the take-home messages that I hope that comes out of today's class, deep learning is extremely flexible. Right? So whatever you come up with, it's like let's integrate those two and then put this and then remove that and then optimize the whole thing. You can probably do it in deep learning. Whereas it's not the case where non-deep learning type approaches. And there is some technical justification because you're doing what's called universal function approximation and so forth. But in essence, what we care about is we have all this flexibility. So all this stuff that you come up with, probably yes, you can do it. And hopefully today you're gonna at least get some keywords so that you can go and follow up on this topic.
Have you ever had the chance to fuse different sensors together in order to improve the resolution?
So this is one that we'll talk about it in a bit. So this, one approach to that is what's called band sharpening, right? So you have even a single satellite where you have two instruments, one capturing coarse resolution but multiple spectral bands and one panchromatic. So the question is, can we apply machine learning and deep learning to do that? Yes. Can we have other types of data and fuse them together and get something better? Yes. In all the cases, the answer is yes. The question is, where do you get the data? Right? So let's say I have one satellite that is very coarse, another satellite which is very fine. It's like, okay, so maybe I can fuse them together and get something which is fantastic. Fine. But the thing that you're going to be seeing today is that in machine learning, you have to say very explicitly. So what is the input? Those two types of observations. Fine. What is the output? My output should look like that. Okay, so do you have ground truth for this output? So do you have this imaginary scenario where your observation is fantastic in terms of temporal dispersion? Probably not. It's not like the typical scenarios in machine learning where you try to classify a cat or a dog. It's like this is a cat. I can tell you this is a cat. If I give you an image like this pixel value here is 73. Is that a good number? It's like, what if I this resolution will it remain 73? It's like it's very difficult to get it down. That's why it's an interesting topic of how to do machine learning and deep learning in remote sensing and not natural images like cats and dogs. So there are nuisances. Hopefully they were gonna system. Okay, so hopefully now it's motivated you that we need to we have all this type of diversity of observation and observation is how can we group them together, and the answer to that is machine learning and deep learning. So this is a slide that I've made in 2020, and what's interesting there is like back then I would say, look, artificial intelligence is going to help us. It's already here, and you have self-driving cars and Siri and all that stuff, and in January of 2020, I was saying that there is this new thing that's called coronavirus or something like that, but don't worry about it because AI is going to solve it. So not exactly, on the spot on this one. So it's just give you saying that so that it's not a panacea, right? It doesn't solve our problems. Though it did help at the end. Right? So if you want to sort of demonstrate what's happening in terms of AI and machine learning, so these are some nice examples here. Let's see if they can play. Can you see them? Right, so those are moving now. So those are deep learning models, where you use one image and ask the system to generate a video. Right, so you generate a video by water. So why is that interesting, right? So it's like, okay, so understand the visual, the aesthetics of this, but what's the point? Because the water goes down. So this is the physical law, the law of gravity. I never explicitly defined in the network saying, what, you have a lot of gravity, so you have stuff falling, they're going to fall down, not up. But the system was able to extract information from the data itself, and without ever seeing, this sequence of a waterfall, was able to generate a sequence where the water was falling down, as it should be, or that the waves follow this pattern. But you can see it's not perfect, right? So you can see that it's trying to do like sinusoids, right? So it's like it's getting some understanding, but it's but it's interesting, and the interesting thing here is not the visual merit of the image. It's fun, but the fact that the system was able to understand some fundamental laws of nature without ever being explicitly told it. So this is an interesting type of emergent behavior. So it's not developed or it's not intended, but it sort of comes up. And now we have all these systems. We're going to be talking about them when you have the ability to manipulate things and make deepfakes and things like that. So of course there is the ethical discussion about this stuff and what you are able to do or you should do or you shouldn't do. But the interesting is in terms of capability that we have this ability of manipulating information this type of complicated information because it's visual information and still be able to maintain something that is realistic and it follows what the human face looks like without ever explicitly defining what the period is, right? So in the case of Elon Musk. And so, that was the state of the art. So I was giving this talk last year. This, I would say, this is the hype example. Now the hype, like in 2023, is ChatGPT, which has been around for like 6 months. It's already a thing. In my mind, in myself, it's a core thing of my day-to-day job. But still, it's very interesting how prolific it is. And so ChatGPT, for those who are, if there's anyone who doesn't know, but it's a program that from OpenAI that's able to generate very realistic type of discussions, and you can think of it as a very good friend that's also an expert on anything, which is fantastic. And you have this, in addition to the natural language processing, the idea of understanding text, you have the same capabilities in terms of generating, images, which again it's much more difficult because if you say here, I have to come up with words and letters. You have 24 letters and you need to, 26 letters and you need to sort of, arrange them in an order so that it makes sense. In this case, you have millions, right, of pixels, but you have arranged them in a way that makes sense. And the idea here is that, you have this capacity of actually introducing one text, here a text prompt, say, generate an image of an astronaut riding a horse for the realistic, and it does that. Right, so it's able to understand the semantic context of this text, plus whatever things mean, whatever a horse mean, whatever an astronaut means, and how they can physically, group together. Again, without ever explicitly defining, but if you find the astronaut and the horse, it's usually the astronaut sitting on the horse, not the other way around, right? So you don't need to define any of this, but the system is also able to come up with ways of producing this, which is amazing. Don't believe people what they say. Nobody has any idea why all these things happen. It's like I can tell you, it's like there's a million different number of parameters, and I can tell you the values, but will not give you any closer in understanding what's happening. So nobody has any idea what's happening. Not the guys in OpenAI. Nobody has any idea. It's happening. Retrospectively, we can ask what's happening and understand some stuff, but what's doing it's somehow embodied internally into this billion set of parameters. So if you want to put it in a context of the brief history of AI and machine learning, you could start from the beginning of this topic in '56 at the Dartmouth College, and then for me at least it was a very big milestone, the Deep Blue, where you have an AI type system beating Garry Kasparov, the champion in chess in '97. And then what happened? A few years in 2016, we have a system like that beating the leader, the champion in a game called Go, which is supposed to be extremely difficult, an order of magnitude more difficult than chess. Then in 2018, we have a situation when an AI system won a tournament in poker. Poker is more interesting because those games are called perfect information, because you see the board and both players know exactly the same stuff. In poker, you can bluff, right? So you know what's your card, but you don't know what's the other guy. So being able to capture this as well in a machine learning and in a deep AI system, yes, okay, check that. So it's already, it has already been demonstrated that an AI system can actually do that and counter the bluff and understand the bluff and eventually win the championship. And there is an exponential increase in things happening now, right? So there are like a lot of people in YouTube that make a living just presenting what's happening in AI in the past week. So there's like a huge amount of things happening there. So when we try to put them together, so we have this term of AI. So out of this AI, there are two big terms. The one's called symbolic AI, and the other's called data-driven AI. So this is the one we're going to be talking about. This is the one where all the hype is. Data-driven AI or machine learning. So machine learning is a subtopic of AI that is developed driven by data, not by rules, formal rules of how to do things. And in this case, you have three big classes. You have what's called supervised learning. So the idea is you're given an example to the system, and you know exactly what the system should produce. So this is supervised in the sense that I know what should happen, and I can quantify the performance of the system based on how well it predicts that. There's this unsupervised setting where I'm not exactly sure what should happen. For example, you're going to see a situation where you put a random number and you expect the system to generate a human face. And randomly, initialize human face that should look like a real face, but I don't know exactly. It should be any real person, right? So in this case, you don't know exactly what the system is trying to do, but you have some ways of characterizing the quality of what's driving. And then the third class is what's called the reinforcement learning, which is somewhere in between. So it's not like for everything you do, you know what's the best thing. So I'm giving you the image, you should say it's a cat. If you say it's a dog, that's a mistake. So that's the supervised. The other is the unsupervised. I'm giving you an image, decide whether it's a cat or a dog, or whether there are cats and dogs, or whether there are cats and dogs and tables and chairs and people. It's like it's up to you to organize, to structure the information. And there is the in between, which is called reinforcement learning, where the idea is, I'm not telling you exactly what you should do, but once you do a lot of steps, I can tell you whether you're able to succeed in what you're trying to do. It's very case in robotics. So in robotics, you have a robot here, and you say, what stuff from here go there, and the robot will do stuff, will move the wheels and circles, and eventually will get there. So it's not like every time it does any action, you can say good move. You're going to say, okay, so you were successful, you were able to reach the other side of the hole. If you fail, you say that. So this is somewhere in between. We're going to be talking about all three of them, mostly the first two. Right, so in terms of supervised learning, so what you know, what the system should be able to produce, the two key scenarios are what's called regression. So the idea is that you have what you're trying to estimate is continuously valid numbers. Right, so you have situations like I'm putting something here, as a matter of time, and I'm trying to estimate the number of, so the CI's extent or something like that. So the idea in regression is that you're given an input, a set of numbers, so some observations, and what you're trying to come up with is a model to predict a standard number, right? So you're trying to see, what is actually the number of, the CI's extent in terms of circles. So produce a number. So this is a problem called regression, where you're trying to produce a number. You might have a situation where you're trying to predict a level. So in this case, you have, for example, two cases. You have images of breast cancer, which is either malignant or benign. And the idea is to identify whether it's class A or B. So you're not trying to get to a sequence of numbers, you're trying to get to select out of a set of numbers, select this number that sort of represents what you're trying to do. So in this case, we have two numbers, 0 and 1. And the whole idea is come up with a system that can take this image and say whether it's a 0 or a 1. And then I can interpret this 0 and 1 as a being malignant or benign. In terms of unsupervised learning, so in this case, you know what you're trying to do, you know which example corresponds to this type of tumor or the other type of tumor. In this case, you know what's there here, and trying to estimate the CI's extent, right? So in this case, you know what the input is and you know what the output is. You have situations where you don't know exactly what the output is, so you have data representing stuff like temperatures and humidities, and then it's like group them together and group them together so that I have a small number of groups or clusters that sort of represents what's happening, right? But with never being ever sure exactly what the system is supposed to be doing or how to quantify the performance. But it's a way of organizing stuff. So when we go to the things that is the most interesting one, which is the case of supervised learning, where you know what you're trying to estimate with. The key concept here is what's called the k-nearest neighbor classification. So I'm going to tell you about 2 or 3 standard machine learning techniques that were the state of the art a few years back, and then we're going to transition to deep learning. Because if someone starts with this topic today, this is the most flexible and the most interesting and the most highly expected quality return of investment type of thing you can do today. But to get some context, because it's important to understand what's happening in the community before the deep learning, one of the standard techniques to classify something is what's called the k-nearest neighbor. So the idea is you have one sample, and what you do is I'm given an image, and I want to say whether this image is a cat or a dog. So I have images of cats and dogs, and I look which image is closer to the one I'm given. So an obvious question is, what do you mean close? What do you mean one image is close to this image but not the other image, right? But as soon as somehow manage to define this notion of distance, then I can say, what, whenever I have a new image, put it there, compare it whatever other examples you have, and see which one is the most similar. And this will define the class. So you can say, what, if it's closer to the blue ones, so this green one belongs to the class of the blue. And there are challenges with this idea. The idea is that, So how do you define that two examples are close together and you can find distance? For example, what does it mean to have a distance between two images? So this is the process of feature extraction, and it's not obvious how to do that. Then you have statistical sensitive issues. You have problems with respect to defining even the single variable, which is how many labels are you going to ask in order to compare this to the thing that we're talking about, the class you're trying to estimate. And the last thing is that all this has a huge memory requirement. So you have to have a lot of examples in the memory and compare with everything. So when you try to do that in real time, it becomes really time-consuming process of getting all this information from the data that's stored in the dataset. SVN, again, people might have heard about this. So the idea is that you can separate data and you're trying to find a separate hyperplane is all the separating line that is the most robust. And there are ways of doing that with data that are a single line that won't work. I'm going to go in there. The whole idea is that you have trees and forests, so decision trees. So the idea is that you start and you sequentially make questions about the data, and once you reach the end of this sequential question process, you end up with an answer, right? So you start from a specific pixel and say, you know what, for this pixel, what's the value of band 4 and then band 3 and blah, blah, blah. So if I travel through this tree, I'm going to end up in scrub, and I'm going to say, you know what, this is a scrub. Right? So this is the whole idea of trees, and you can have multiple of them. And what you get, if you put a lot of trees, you get a forest, right? So the idea is you have multiple trees and then you average them. And a last one, which is, let's say, if there is a single algorithm right now that's not learning, but it's still standing strong and it's useful and something that people should explore, given the specific condition, is what's called the gradient boosting. And XGBoost is a specific idea of this, where the idea is you have sort of the idea of having a tree, but what you do in the tree is you train a different model. So you start from the data, you generate a model to separate the data or predict what's happening, and then you encode the residual. So what's trying to do is progressively make the system more robust. So this will do very coarse separation classes. This will do a more fine separation, more fine, and eventually, this is gonna produce the classification. So again, if you're gonna try something that is not deep learning, especially if you have data, so big Excel files and you want to encode them, go and check out the gradient boosting techniques like XGBoost. It's fantastic, it's very fast. But in reality, you probably don't have data like that. You have, like in remote sensing, you have images, you have observations, and you have time series, and you have spectral bands, and things like that. And the question is, how do you take all this together and have a system that's going to introduce all this data and come up with the thing I'm trying to do? And if you want to see the difference between machine learning and deep learning, you can, see that here. Right? So the idea is that in both cases, what you're doing is you're taking an input, so an image, and what you're trying to do is try to characterize this image, like predict that this image here contains a car or not a car. The difference between deep learning and machine learning is that when it's machine learning, you have to define what are the characteristics that I'm going to be looking for in this image. I'm going to look for round things, and I'm going to look for shiny things and things like that. And those will be included to understand what's happening. With the deep learning sort of revolution, you don't need to do any of that, right? Which makes it extremely flexible because you can work on any type of data. Take the data, define a neural network model, and say what's supposed to be doing. Train. That's it. So as long as you have data to support this process, you're fine. You don't need to have any very detailed understanding of how is the reflection happening here, what about the specular points and the characteristics of the imaging modality and things like that. It's much easier to work with more data, and this gives the flexibility of combining more data, right? Because the type of features that are important in optical imaging are definitely not important in radar imaging, and vice versa. Right? So what would I do? I need to be expert on both domains, find the most important characteristics and fuse them together. You don't need to do that now. Now, take all the data, radar, spectral, hyperspectral, throw it into a deep neural network, let the system train, and it's going to produce something which is going to be, at least competitive to the state of the art. Any questions or thoughts or comments?
I want this and that. How do you find it?
We're considering find what's like what we're looking for and how it does the system like this work. So
Regression boosting can be used as a sequential decision-making process. I mean, as we go over our data and get results and round through it, then
it's not designed to be like that. So the sequential process happens internally on the residuals of the model. So it's not like your data can be modeled sequentially. It's like these are my data. The sequential process applies to reducing the impact of residuals. So it's happening internally. So no, it's not the best tool to use in sequential data. It's fantastic if you have tailor data, like this is my observation, I want this XY coordinates and I get this type of measurements. And then this type of measurements. So when you have like point-like measurements, so you can put them in an Excel file, a CSV type of data. Boosting techniques, XGBoost, which is the sort of standard, ready to go, ready to use library that's available there, it's fantastic. But if you don't have like specific measurements, and you have images or time series or sequences, then you need some of the stuff. Yes.
How would you address about the quantity of data required to train these models? Because quality data having a cloud server or analytics, they are limited. So for this, we need to train a high amount of data. So how to address this bottleneck or response?
So we're seeing about it under the fact that in some cases you might not have enough data, or you might have what's called imbalanced data. You have more of one class. So let's say I'm trying to do a system that's going to detect floods. So for every 100 non-flood events, I have one flood event, right? So how do I reconcile them? So there are ways. It's not obvious. It's not done here. And right now it's I'm trying to put that in the most professional way possible. People can do very decent professional work if they go to computer vision conferences, see techniques that are developed for computer vision, say, what, this is an interesting technique. If I like my remote sensing problem, it's going to do wonders because it's going to help me solve this. So there is a lot of effort going in the computer vision community that's very easy to transfer to remote sensing community and get your stuff moving in terms of handling small amount of data and things like that. Yes.
one question about a problem that how to choose between very much learning or deep learning. But we know that in terms of computation and facility models, investment of managed data of the complexity I need to have to justify that I go for the learning and computation. Just your idea about this.
Today, if you're going to start a project, start with deep learning. If you don't have enough computational resources, ask your manager to give you a better GPU to get more computational resources. Right, so you can do stuff with all that, but then someone else is going to come up with a technique that uses deep learning and get better from the right? It's up to you. But we're going to see an example where you can leverage a lot of money that has been spent in training a system to classify cats and dogs and say, what, if I have a system that's been trained on 10,000 cats and 10,000 dogs, then maybe with 10 examples of an airplane, remote sensing airplane and ship, it can do just as fine with just a couple. And we're going to see example today, the second part that indeed, you get huge increase in performance by leveraging what other people have paid for now.
I wonder if people are using physics-informed machine learning for remote sensing applications specifically. I know they are using it in different fields where they gather information from mathematical models, such as partial differential equations. I wonder if there's any use in remote sensing as of now.
Well, I'm definitely there are at least 4 or 5 pages that guide with titles that sort of resemble what you're talking about. But this is the mainstream topic that people spend time doing that. No, and it's I think this is an excellent comment. I mean, if one of the things that would be interesting in this today's talk would be, okay, so machine learning and deep learning, okay, those are fantastic, but eventually we spend so much time developing all these physical models, and a lot of people spend their careers doing that. So now we're in the situation where we have the low hanging fruit, so you can do a lot of stuff with data-driven models, with understanding the physics. In 2 years, that we're going to have sort of the same meeting, it's going to say, what, guys, now the low-hanging fruit are pretty much done. Now we need to invest something. And what we're going to invest, we're going to invest in our expertise in the domain, which is the remote sensing. And there are different ways of using the ideas of information about the physical process and the deep learning. We're not talking about any details, maybe a couple of slides at the end, because it's a big topic, but it's still in the infancy, right? So there is still a lot of room there to Taylor-Feber model. As you say again, in physics, in astrophysics, for example, it's because the equations are easier. There's not a lot of parameters. So you try to estimate something now, you have like 15 parameters. In astrophysics, like the whole universe is 8 values. Right? The lambda CDM model is like 8 parameters, and that's the whole universe. Right? So people use it there, but it's something that I think gain a lot of traction in the few years. Yes.
Maybe don't use this model. A way to see which feature is better than
for example, right? So if you do feature extraction, you're going to say, I'm going to take my observations, and then I'm going to have like my digital elevation model, which is going to say the height, and then I'm going to have the slope, and then I'm going to have the spectral expanse, and then I'm going to say, my machine learning model, out of these 15 features, which one is the most important? Machine learning is going to say slope. Slope is the thing we're interested in. In deep learning, if you're going to do that, it's going to say neuron number 4076 has a value of 92, and that's the most important thing. So you don't get something that is, physically meaningful to us as humans, that has some semantic context that you say, you know what, this is the thing you find most interesting. It's a combination of numbers. So if I tell you the numbers, how close are you to getting the understanding of what's happening? And this is, applies to all deep learning. Right? So if you say, what, maybe I will apply my feature extraction model that I know of, and then I'm going to apply deep learning. Probably not as good results and when you apply deep learning natively. Because what you lose if you do feature extraction beforehand is you don't have what's called an end-to-end trainable system. So in this case, this is the input, this is the output, let the whole thing to do this job. In this situation, this is optimized task for feature extraction, and this is optimized task for classification. So it's not necessarily the features that were found here are optimal for classification in the specific classification setting that I'm setting, or vice versa. Right, so you are probably doing two processes independently, will probably not get you as far as doing one process at the same time. Now, if the question is, well, I know a lot of physics about my models, think about how you can use them, in this deep learning model and write a paper, because as I said, it's a very hot topic, but it's not open. All right, so let's continue. So, deep learning, right? So deep learning has been, initially it was developed in Stanford in '58, and it was a hardware. Right? So the method of the machine was a machine with polygons. It was like a feature machine. And then they decided that what it's actually software. Right? So we have this, the algorithms, and then from so forth it's algorithm. One of the things that has been like instrumental in finding this domain and this explosion of deep learning was the whole idea of convolutional neural networks. We will come back to analyzing images we're going to talk about today. So they were invented in '98 from Jan LeCun. So Jan LeCun is one of the grandfathers of deep learning, right? In '98. But then nobody cared about it. Nobody cared about it because the complexity it took to train the system was like prohibitively large to have any meaningful or state-of-the-art type results. So nobody cares, and they applied different techniques. And that all changed in 2012 when this, paper Alex was able to beat all other machine learning models in this ImageNet challenge. This ImageNet is a collection of some 1 million images of different classes, a couple of different classes. So it was able to demonstrate that this is state-of-the-art performance. And to do that, they were the first to introduce GPUs, like graphical processing units, which is the go-to hardware today for the system. So before that, you really need to be like a GPU programmer in order to do anything. And even though still was difficult. Nowadays, it's nothing. It's built-in. So the systems or the languages assume that you have a GPU. It's not necessarily a GPU. You can work around without it, but they assume it's like almost trivial to engage the GPU version. But then that was not the case. So when they actually did that, it's state of the art. And then from this on, it was like it's really crazy. Right? And if you want to still say, okay, so out of all this craziness, what are the big classes of techniques that have been developed? One would say there are two big categories. The one is the convolutional neural network, CNN. So this CNN are developed in a way that they take, for example, images and they can produce labels. So this image is the image of a car. So they develop convolution and CNN. And they can take an image and produce a graph, or they can take a noisy image and produce a clean image. Right? So you can do stuff like that, like take images that don't necessarily say what they contain, but produce other images that are better quality, for example. So that's the one black class, the convolutional neural network, which exposes the whole idea of convolution, which is looking locally at an image and see what's happening. The other state of the art is the RNN, or the RNN and the LSTM. So those two techniques, what makes those different compared to this is that they have the whole idea of time. Right? So if you have time sequence, time series data, or you want to somehow include the fact that they have stuff that change over time, you need something to involve this capacity of memory, remembering stuff, right? That's how the notion of time translates to a system, that it is a memory. And this RNN, the recurrent neural network, and LSTM, the long short-term networks, they have this notion. We're going to see more details next hour, probably. But they are capable of encoding, evolving stuff. So this is fantastic when you have studied a big type of data, like big images. This is fantastic when you have sequences of information and capturing these temporal dependencies. But all this is now sort of trickier because the state of the art now is transformers. Right? So this is a technique that is fantastic at both of them. It's great. Everybody's using all the big high-end DALI and mid-gen and all these models use transformers, ChatGPT uses transformers. We're not going to be talking about transformers because now the domain is although it is prolific, it's very early in terms of theoretical design. It's very difficult to use. So if you have Google type of resources or Amazon type of resources, fine. But if you're trying if you are a lonely researcher trying to do your job, then it's not going to be easy to do transformers. But the whole idea is that you first understand those topics, and then you say, what this new type of concept has to offer. But this is a more advanced topic. So we're going to talk about it, but not that much. So the two standard things that people use in the 90% of the cases, at least in the case of remote sensing, are convolutional neural networks, where they have images and spectral tubes and things like that, and RNN or LSTM, where they have time series type information, and they want to encode the time. Yes, please. So there is one slide talking about transformers. So so this is interesting, I think, take on this. So in the convolutional neural network, the whole idea is that if I'm looking for stuff that's happening in an image, something that's happening in this region will probably is related to something that's happening nearby. So if I'm trying to have a face, an image of a face, if I have a round thing, I would expect to have another round thing, and then maybe a vertical thing, and this is sort of a face. So this idea of convolution, of having stuff that are locally correlated and exploit that, is interesting. RNN, on the other hand, says, what, we have to encode sort of like a memory, something that changes over time. So what is the most obvious mathematical framework? Markov chains. Markov chains are designed so that you remember stuff. So let's do that. So they realize that. Now transformers, they do none of that. Transformers say you have no idea what's going to happen. So express everything as vectors and then take linear product between this vector and every other vector in the universe. And that's about it. Why do you care? Because if you do that millions of times and you are like OpenAI, then you have ChatGPT. That's as simple as that. ChatGPT, the underlying idea is that I say something, say a text, I convert this text to a vector, somehow it's called tokenization as a vector, and then I have millions or billions of other vectors, inner product, so this is called attention, but it's inner product, and this is the thing that you need. So it doesn't include memory, it doesn't include convolution. So instead of saying that we have no idea what the system is doing, it says, our system has limited inductive bias. So inductive bias in the learning system is the assumption that you make when you design the system. For example, if I know that I'm going to be processing images, I know that stuff that are close by should be related. So I know that, and I'm going to use convolutions. So this is inductive bias. Use your prior knowledge to modify. This, because they have no idea what's happening, says, we don't have inductive bias. So this is an interesting case of how you make a shortcoming a feature. So instead of saying we have no idea what's happening, say, no, it's a feature because we don't bias the system. But very difficult to do anything with transformers yet. It's lots of parameters. So in order to get something reasonable in terms of performance, you have to scale up really big. So it's complicated. It is, if you look around, there are papers that do transformers for most of the stuff we're doing today, but it's like 1 or 2 papers. Whereas in the convolutional neural networks, like 100 papers doing that. So it's a much more established and thought out and investigated topic compared to transformers. But in 3-4 years, this small transformer will be really big. It will be up to date. And when can we utilize deep learning, any of these techniques in machine learning, in all of them? It's like anything, right? So we're going to see scenarios today, but you can go and find papers in Google Scholar or Archive that's going to apply deep learning for land use classification, object detection, text detection, climate distribution, property, damage, biomass, planning, surface water, atmospheric gas, land, forest fire, anything that has been traditionally explored in the remote sensing community cannot be done with deep learning. The only requirement is you have the data. And when I say you have the data, the most important thing is not you have the input data, because the input data could be satellite data or like drone type of data or in situ data. What are the data? So when you try to do forest fire detection, so this is the satellite. How do you know that this area here is the forest fire? Who's going to say that? So this usually involves people doing that. And people have been already doing that because you didn't have machine learning system like that. So, why it is that we can leverage effort that people have put in, creating disaster response maps that did by doing an image distribution like glass and magnifying glasses, use that as training data to train machine learning models and minimize the latency between getting the observations and the analysis, right? But you can go, out of this, there are at least 20, 30 papers published in IEEE papers on this topic on them with deep learning. So it's new, but it's probably and some of the scenarios we're see or are interesting and has been experienced, is for example the case of scene classification, right? So this idea is so you have a drone or a UAV or an airplane getting the images, and what you get the type of information you get. So this is the AI data set. So the data set, the type of data you get is you get images like that and labels. So this image is industrial, this image is desert, this image is church, this image is bit. So you associate one image with one label. This image is this. So you have a different set of labels. So you have building residential and forest and blah blah blah. So you have 16 or 100 classes, and you need to pick one. So this is the problem of scene classification. So you can sort of express mathematically like that. So you have the input X with an image. So an RGB image is something like M times the spatial resolution times 3 color bands, red and blue. And you're going to take this, and you're going to put the system is going to produce Y, which Y is one number out of a set of K numbers, where K is the number of classes. So each image responds to a specific class. So this problem is generally called scene classification. And then you have the classification where the observations are not from an airplane, but from a satellite. So a couple of very prolific data sets that exist right now is the GRSS. So this is a data set that took a lot of effort to generate. And what you do is you have observation from Sentinel-2, so that's red, green, blue, or multispectral or information. And then for every image you have a land use, right? So every box here corresponds to a different land use, like forest and trees and beach and stuff like that. So it's 64 by 6. So you can imagine the input has been 64 times 64 times 12, so 12 spectral bands. So the image in this case is 64 times 64 times 12. And here you can find one of the classes that is associated with it. So this is the Eurosat dataset. The SO2SAT dataset is similar, extended in the sense that you have multispectral and radar. So you have SAT and MSI. So what you do is now you have two types of observations. You have X1, which is M times M, which is 32 by 32 times 12 spectral bands from multispectral, and 32 by 32 times 2, which is the vertical horizontal polarization of SAT. And you have two types of data. So you're going to have a system that takes both of them and again produces one label out of this class. So sparsely built, lightweight, low rise, open mid rise, all these type of land cover abstractions. And the idea is if I have a system that can do that automatically take observations like that and put like that, I can apply it to the whole plan. Right? So if I have a system that's training a diverse enough data set, I can apply the whole plan, and I have a system continuously seeing and monitoring and quantifying land cover and land cover changes. And there is also the big net. So this is an investigation. In this case, you have Sentinel-2 observations. So each example is 120 by 120 pixels and 10 meters, so they look like that. And the difference between this data set and this data set is now we're not trying to associate every example, every image with one label, but with multiple labels, right? So you see here in this image, it's characterized by, okay, so for example, so this image is characterized by permanently irrigated land, vineyard, beaches, dunes, sand, waterfalls. This one, permanently irrigated land, beaches, dunes, sand. So there is a lot of keywords that characterize, there is a lot of attributes that characterize each image. And this is, one would argue that this is the most interesting case because it typically represents the scenario where you have an image that contains a lot of stuff. So you need a lot of textual information to describe what is textual file. And so similar situation here, you get an X, which is in this case 120 times 120 times 12, because this is Sentinel-2, so 12 spectral bands. And what you do is, the labels now is not one specific label, but it's combinations, right? So you can imagine that we have a little dictionary of different types of characterizations of the images, like 1,000 different labels that I can assign to these images, and then for every example, I need to pick up the smallest numbers of labels that truly characterize my observation, as it's here, right? And whereas in this case here, that it's going to be one out of the case, so this is going to be open low rise. That's it. There is no other alternative, right? So if you find that this image is an open low rise, that's fantastic, 100% accuracy. In this case here, it's more difficult because what happens if I have this? And I did find that it's a coniferous forest and a mixed forest, but I don't find water bodies. And so I don't characterize water bodies. So it's like 2 out of 3. It's not the same as taking this image with an open highlight and saying that it's expansive. So that's a mistake for sure. But in this case, you might have mistakes which are more difficult and more nuisance, right? So you might have one label missing or an extra label presented there. So the question is how do I tell my model? And again, this is not an obvious problem and setup. Which again, you apply your deep learning models, and we're going to see examples where you apply your deep learning models and you get all this stuff by themselves without ever explicitly encoding the fact that like agriculture is sort of related with this type of values in the NDVI, which is the standard feature. Another type of application is object detection that we can do, right? So in this case, we started from you have the satellite and we take this time, this region, and say what characterizes this, either with one label or many. And then we say take this and then characterize, identify things of interest, of my interest. So in this case, here you have object detection, so you try to do both detection, and you have sort of 2 scenarios. The one scenario is just make sure that you put a bounding box around the region, that's fine, right? Or they have situation where you have to be more specific, like rotate the bounding box, make sure that it fits in terms of size, make sure you have more detailed information. But in any case, in both cases, what you're trying to do is you're trying to get an image and then identify all the specific realizations of this particular object you're looking for. None if you don't find any. Right, so in this case, what you do, you have an image, which is the time times m, right? So it's x and y times 12 spectral bands or 3 spectral bands. And what you try to do is you try to find potentially bounding boxes, right? So you have a set of bounding boxes that you need to identify and potentially classes, right? So when you have an object detection, I might have a system that is designed to detect 10 different types of objects, like cars and boats and trees and things like that. So you might give an image and identify multiple of these, right? So in typical situations where you have bounding boxes and class. So in this case, it's like bounding box, so potentially x and y or some other ways of encoding this, plus the vector function there. That's a goal. And then object detection is an interesting problem because it has been heavily investigated in the computer vision community, but it's not the same as the remote sensing community. And these are just some examples of what's the difference, right? So when in the standard, what's called natural images, the images we take with your smartphone, you talk about the plane, it usually looks like that. This is the usual image of a plane where I have like with a commodity, with a non-scientific like context. And this is what I get remote sensing, right? So these are aerial images, they have specific characteristics, the variations are specific, the sizes, so it's very difficult, right? So when you have images from a smartphone, it's usually half the image contains a car. In this case, you might have a few pixels containing the car. So you have a lot of challenges that go into deploying these object detection models to remote sensing data. Other things you can detect, which is like more obvious, like okay, so you can detect, for example, clouds. Right, so this is a scenario, for example, where they have 38 plants are negative images, and these are red, green, blue, and the near infrared. And what they try to do is try to come up with maps like that when black pixels correspond to no cloud and white pixels correspond to cloud, so they give colors. So there are obvious techniques of doing that without any machine learning models. There are ways of doing that with deep learning models. But the potential of deep learning models in this case is that you can have a situation where it's not like 0 or 1, it's not cloud or not cloud, but you can have like a more of a continuous value, say how cloudy or how hazy it is. The challenge in this case is how do you find the ground truth data to train such a model. But in this clearly has been applied, there is a situation when this thing we're going to talk about it later today, where they apply this technique on board the satellite itself. So the satellite would take an image, would apply this deep learning based cloud detection, and say, what is in the context of more than 20% cloud, so I'm not gonna throw it away. I'm not gonna compress it, I'm not gonna store it, I'm not gonna transmit it because it's useless. Right, so cloud detection, it has a lot of merit, whether it's more efficient to do it with deep learning or not deep learning is another thing, but it's definitely explored in this context. In general, the whole idea of object and target detection and recognition also covers a lot of other application domains. So you have situations like detecting smoke cover or detecting oil spills, or more human anthropogenic, let's say, construction like solar panels, detect volcanic eruptions, active files. So this is the thing that we're going to see later on as well, or like floating plastic litter. So there's a lot of stuff that we can put under this umbrella of object detection and classification with different characteristics, right? So its scenario is a difference in the terms of it's not like natural images finding the cats and dogs. You have atmospheric effects, you have the characteristics of the thing that is of interest, you have visit frequencies and so forth. So it's a complicated process, but these techniques apply there as well. One of the other standard techniques is not take an image and find stuff, like this scenario, take an image and find me boats or planes or clouds or oil spills and volcanic eruptions. Another scenario is take an image and tell me for every pixel in this image, associate its class. Right? So this is a problem of segmentation. So in segmentation, what you do is you take an image, so for example, this is RGB, so this is an n times n times 3, and you have to assign every pixel of this to a specific class, right? So if you produce a new image, also going to be n times n, but it's pixel there, it's not going to be like an observation, but it's going to be an integer value from the consistent number of classes. So in this case, we have how many classes? Land, building, vegetation, road, and water. So 5 classes. So each pixel is here 5 different values, and this is the pseudo-coloring scheme of these 5 values, right? So in image segmentation, you assign every pixel value. In object detection and classification, you try to identify one region that contains the thing of interest. In scene classification, you're taking the entire image or the entire scene and you try to annotate this and get information about this. Right? So depending on what's the resolution that you're going for, you're talking about a different problem. So this is image level resolution, region level resolution, and this is pixel level resolution. Right? So now we're working on specific pixels and try to estimate their values. And other things in remote sensing, when we talk about segmentation, it's done grammar and drop type classification. Obviously, there are many more stuff that you can classify and associate with pixels, because in our case, remote sensing, each pixel corresponds to the next byte coordinate on the planet. So if I'm characterizing this area of the planet with something, I can most definitely do that for every pixel in the image. So you have scenarios from associated different groups, or scenarios where you have 5 different classes that have classes, and I'm trying to assign every pixel one of these 5 classes. A very prolific application in terms of machine learning and deep learning for automating the process of assigning each pixel a label. Another scenario also of interest, and I would say it's sort of unique in remote sensing. It's not something that we find in natural images. Is the scenario of change detection. So the idea is you have multiple observations, you get it over time, and what you do is you try to find the before and after and compare those 2 images and find any changes, right? So this is, I think, one of the most interesting applications for deep learning in remote sensing, because it's unique to remote sensing. You don't find that with natural images. With natural images, you take an image, then you take another image for the point of looking for change. But in this case, because you have global coverage, you have everything georeferenced, you can monitor things over time. So you have situation, this is the before, this is the after, and you want to try to do is you try to have a system that takes those two as inputs and try to identify to get a map like that, where every white pixel corresponds to something that is different. And the application is endless in this case, but the challenges as well. So you have challenges related to atmospheric conditions, so hazy, not hazy, sunlight, reflections, resolution. So you try to find something changes maybe is too small to be captured by pixels, or maybe my resolution is too small, so that changes are the smaller of pixels, so it's difficult to see. Modality, what happens if my before image is from optical and my after image is from radar? Can I do something with this and then still come up with this? But I think the most striking challenge in this is the lack of ground truth, right? So if I have the before and after, how do I know that for every pixel this change or not? And what does it mean for the change? For the change might be a change in terms of a different type of cultivation might be a change. Moving from cultivated land to pavement, that's a change, right? So how do you define the change? It's not obvious, and this is a very interesting challenge for the scenario. Image noising, you have images that contains noise, and you're going to get an image that doesn't contain noise. So this is a change in gear, right? So in all the previous settings, you have images and you're trying to get bounding boxes or values. In here, you have images and you still get images, but they are different images. So this is the input, this is the output, this is red, green, blue, and this is labeled, so it's different. And you move to the third case where you have images going to images. So this is a red, green, blue image, and this is a red, green, blue image. So you stay within the same domain from images to images. And one scenario is I have noise and I'm trying to remove this noise. So you can express it like that. So from images to images, but try to remove the noise. I have a small image, try to go to a big image. That's another case of super resolution. So you're trying to increase the spatial resolution in this case. Compression, I have an image, I try to do it in a effectively binary format that it's much more efficient to store on transmit from the satellite and being able to reverse this process. Also another challenge. And fusion, this is something that we talked about. So what happens, for example, if you have low resolution color and high resolution monochromatic, right? So how can you group them together to get something that is the best of both worlds? It has both color and both high resolution. So two observations here, one out. Forecast. This is forecast. You have previous observations. You try to predict the next observation. So this is a very interesting stuff, right? So you have something that changes across time. So n times m times t times steps, and you try to predict the next time step, and you can do that multiple times. So this sort of captures now the type of problems you have from remote sensing data. Any questions or thoughts on or ideas on that? Yes, please. What is the application here? When the idea is that you have an image and you're trying to find potentially if there is a small region that is associated with the thing I'm looking for, it's typically an image detection or an object detection. So you're trying to detect this target, which is the oil spill. So typically in the oil spill, this is how people have addressed that. Now, if my resolution is so big that the oil spill is effectively the whole image, then it's an image classification, because my image will be either an oil spill or not an oil spill. Right? So you have two different settings. But it's usually a big area, and you try to find a small bounding box. So it's usually a problem of detection. Yes.
That it is a classification problem, but the targeted class can be more than one. So that in the data set, is it that it gives the percentage of pixels that belongs to one class or
0, 1. Does it contain this? Yes or no?
Oh, so it would be a string of 0, 1. One means that those classes are there.
Yes.
Yeah. You talk about the noise. So what's the concept? How you are doing it? It's like, are you saying like, this is noise, it's not noise, or how it's?
You introduce a noise image to the neural network, say, you know what, this is a noise image, and what you need to do is you need to come up with this, which is clean. So this is something you have pairs of clean noise image trainers. You somehow must find your noisy and non-noisy examples. Which is a big question. What you usually do, because you don't have that, is you take clean image, you add noise yourself, and then say, okay, so let's see how well it does it in covering this because I have my ground truth. But it's not realistic because you add the noise is not there. So I think one of the most interesting, challenges in deep learning and remote sensing is how do you find the labels, right? So if it's something like detect orange speed, so someone can sit and say, you know what, this is the orange speed. I can annotate, I can find it, that's fine. But these are problems like denoising or enhancement or things like that. How do you know exactly whether this value here should be like that or the other? You don't. So it's an open-ended process here. Yes.
For my case, I would like to detect the shape. So if again we apply on image emoji, we will make it block a lot of the shape, right?
Yep.
So I don't know when we can apply that.
Well, this is an interesting project, right? It's not obvious. It's not like there is this code in GitHub, download it, run, it's going to work because you need to somehow remove the noise, but also make sure that you don't miss the information that is related to the shape you're trying to do. So it's not obvious how to do it. Yeah, it's not obvious. One way would be first the noise and then detect. Is that the best? Probably not. You can do it, sort of fuse them together, simultaneously enhance and detect. I don't think there is any neural network off the shelf that can do that. So those are sort of independent problems, right? So the noising is I have the image that has noise and it has to be removed. And then I'm going to end up with a clean image, and then I'm going to apply any type of other learning algorithms, another neural network that's going to detect the shapes and so forth. So you can do it in 2 steps, for sure. Is the question, can I do it in 1 step? Because I don't think you can do it in 1 step. Is that the question? Am I following? Yes.
In the right image for the detection of cloud. So in that, how is download being generated? Like how are people
annotating cloud? People manually annotate cloud. It's like images and then there are students go then it's like cloud, so this is download.
But in the images there are some cases which are manually also not distinguishable, and is it cloud or not? In that case, what else?
Good point. So the best you can do in any machine learning model is match your training data. So if my training data, I'm not trying to do cloud detection, and I have 2 types of data. So I have observations, and I have 2 types of annotations. One from a high school student who doesn't understand exactly what cloud is, and one from an atmospheric scientist who is like very expert. You would expect that the annotations you get from the expert are of higher quality. So if you train your system in this higher quality, you would expect the system to perform better. If you train your system on some kids, let's say annotation, it's going to be just as good as the kids annotation. So you cannot have double standards, right? So the same way you generate your training data, that's the same way you need to validate the performance of your system. Otherwise, it's unfair. But yeah, obviously, getting the ground truth. I mean, the world is not 0 or 1. It's not like we're going to have an image and then magically the cloud is going to go away. It's not like this pixel here is black, whether it's pixel is white. Doesn't mean that in 10 meters difference on the ground versus cloud and no cloud. You have to draw the line. I mean, you say, you know what, this in my view, this is where the cloud stops.
Do you have any thought in deep learning? Do you create different type of format of data? For example, you talk about like having satellite imaging or even satellite. Is there like having like satellite imaging and photography imaging from the ground and like text data? Is it like possible to do that?
This is definitely the beyond state of the art part. So try to see whether I can fuse together text and images and satellite and area and all together to get something. This is something that's like the forefront of research now, right? So this is the most interesting stuff you can do right now with deep learning and remote sensing, but it's not done yet. So I'm going to show you some examples where you can take, remote sensing images and do some, like, produce some text that describes them. But it's some early ones.
Data, ratio mapping, and cloud issue there, cloud governance. So one issue is to remove it, another issue is to what's beneath it to that information. So is there a way to generate that? I mean, this will help me to get the cloud, right?
But you like to understand what's happening.
This means that we need that.
So if you are okay with the assumption that my satellite is an optical satellite, cannot see below the cloud. So I'm going to put something there that looks reasonable, but it's not measured because I cannot measure. But it's reasonable and I can do my job. If you are okay with this, then on part 3 of this, we're going to talk about how you can use generative cellular networks to produce that. But again, you don't have measurements there. You are estimating something. So the system can estimate all sorts of stuff. So how do you know that the quality of this estimation is good enough so that we can introduce it in the rest of the pipeline? So, take it with a grain of salt, but there are ways that we're going to talk about how we can do that. Exactly. Yes.
Mentioned is classified into more than one class. Wanted to know what are the possibilities that can be used can justify that this belongs to this class, then the other class will be classified.
So the way that this image is produced by humans, some will say that this image in my view is characterized by this only. Someone would say this will be characterized by these 4 different things. So this is the human. So the best you can do is the ground truth. So if the ground truth is designed by humans, and humans say that, then this is the best you can do. And this is how you should develop. It's not, it doesn't, and you have situation, for example, in natural image classification in ImageNet, humans have a 95% accuracy. It's like, but it's images of cats and dogs. Why? Because there are like 10 different breeds of dogs. And you might be mistaken, right? So there's a 95% threshold or ceiling there. You cannot go above that because the system is noisy at that point, right? So yes. Yeah, forecasting. So when you do numerical models, you solve the PDE and you solve it for time steps, and you say, what, the more time I allow the system to run, the more it's going to be producing. In machine learning models, when you do forecast, it's usually one step ahead. So one step ahead is if my temporal resolution, if my bins are like 6 hours, so I'm trying to do forecast every 6 hours, I'm going to do, use the past 36 hours to do the next forecast for the next 6 hours. Once I have this forecast, I'm going to integrate it with the historical and do a next forecast. So I'm moving one step at a time, every 6 hours to do the production. And I can do that, forever. The quality drops, same to numerical weather models. But the whole idea is you do typically one step at a time. So you produce one, and then you use that as an input to the system. So you produce the new one, and then produce over and over and over, and because you can do it so many times. So that's usually the idea. So the idea is like one step at a time versus predicting 10 steps at a time. So it's typically one. So instead of saying 10 time steps at once, predict one at a time and do it 10 times. Yes. Yes. No, you don't have to use anything fancy. I mean, the prediction for the network itself is just another value. So if I'm predicting Thursday, the system doesn't know if it's a prediction or if it's a ground truth. So if I'm introducing there, it's just going to predict something new. So it doesn't care whether it's predicted or. No. You don't have to change anything. Just reapply. Okay, so we're gonna have the break. Let me do this. So the most remote sensing data we talked about comes from this scenario where you have satellites. There are 2 also very interesting scenarios that you also need to integrate. The one is how do you take measurements from the ground in situ with the characteristics and properties of having in ground measurement. And how do you exploit numerical models that are very robust and a lot of mathematical physics there in modeling them. And then in terms of getting data, I'm going to stop and I'm going to give you some examples. So, so it's always this data. What do you get them? So this is the practical point of view. So for example, Copernicus organized data produces all the Sentinel for free, and you can download them. There is the Alaska Science Facility, so this produces smart. There is the USDA, so you probably know this, that you put them together. EO browser, this is the European Space Agency type of application for Sentinels, so radar and spectral, fantastic and very nice, very easy to use. Worldview, sort of the equivalent from NASA, also great. And Google Intelligence. So Google Intelligence is, sort of analysis on this domain because it was able to integrate like huge amount of data under one roof with a very nice one specific API to get all the data and do the analysis. So it's fantastic. Yeah. So that's it for the first part. Any questions or ideas for the data? Yes.
You showed the data set for classification. Are there such data sets for segmentation as well?
Because what we're trying to segment, for example, if you're trying to segment land cover types, so you're trying to assign everything set a different land cover, which is a very natural application that are many data like that. Like problem classification or like technical, application belongs to water or no water, forest or no forest, stuff like that. Lots of data. And these are just some examples that I showed you there, which is data. Something that I should have included, but I didn't. What we sort of talked about yesterday is that there are now services or like sources in the data sets that are ready for machine learning. So the input and the output of the system is already there. So the Radiant Foundation is a big source of data that curates all this data. The stack things that we were talking about yesterday. So this, the stack framework is fantastic because this RNN, which is the organization that formulated this. You can put it and say, okay, this is the input and this is the label, right? So flat, no flat, forest fire, or whatever you're trying to find, get in there, download it seamlessly, and then use your machine learning model. So, GitHub also huge amount of data. So there is a difference between data sets, data, and data set. Data is where a human find the observations, which can be anywhere. So all these are data sources. Data sets are stuff that are have been organized and curated so that you can apply it in the machine learning model. What does it mean? The input and the output are well defined. You're going to take an image and you're going to find class. You're going to take an image and you're going to answer pixels. So this is well defined in the data set. In data, it's just measurements. Any other thoughts? Yes.
You should just go to the slide where you classify galaxies into spiral and
Yes.
yeah, so any idea? I mean, these two are the basic classes, but there are many more. So any idea how the performance is for where actually the number of classes are more?
So that's a fantastic question. If I have a neural network that has been trained to give images of cats and dogs, and I give it the image of a desk and say what it is, the neural network is going to see the desk and say, you know what, it's brownish. Most cats are brownish. I'm 100% sure that this is a cat. It's going to be 100% sure that it's a cat. In fact, neural networks, the more wrong they are, the more confident they are. So it's definitely, and it's true. I mean, if you think, if you see like that's like, like okay, for some reason does it look more like a cat or more it looks like okay, so it looks more like a cat. So for the neural networks to say, oh, this is a cat. What you're talking about is the problem of saying, I don't know. This is not a cat or a dog, this is something else. This is definitely an open problem now. Open-ended classification, incremental learning, never-ending learning, online learning, all these are different keywords of techniques that can apply this. And the whole idea is I might have something that is what's called out of distribution. So I teach the system to classify cats and dogs, and then I get the test. So this is something different.